All right, hello. Welcome to my channel. This channel is for educational purposes, and we learn about different obscure theories of everything, more or less. And today is video number 214 on the reciprocal system of theory. And this is a theory of everything, or system of theory, which was invented by Dewey B. Larson, maybe discovered by Dewey B. Larson. And Mr. Larson died back in 1990, but he was working on his theory for about 60 years before that, and put out many books and articles and gave a lot of talks. And the basic idea behind the theory is that we live in a universe of motion. The universe is made out of motion, and motion is the relationship between space and time. It sets up a generalized reciprocal relationship between space and time, hence the name the reciprocal system of theory. I'm sorry if you hear somebody out there using a big leaf blower, but that's the way it goes. And we have a generalized reciprocal relationship between space and time. Space and time are not the container of the universe. We tend to think of space as being kind of a container, that the actions of the universe are going on in space. And while you can say that, really in Larson's system, space and time are actually the contents of the universe. So everything is made out of space and time. Space and time are both the same. They are identical to each other, except that they are reciprocals of each other. They have a relationship that's similar to a fraction. If you think of motion as the fraction, space or time is the numerator, and time or space is the denominator. But it is a little bit more complicated than that, because space and time both have their coordinate aspects, meaning that they both come in 3 or more dimensions, XYZ coordinates or WXYZ coordinates. And we generally recognize that space has 3 or more dimensions, but we don't generally recognize that time has 3 or more dimensions. Now, what we do recognize about time is that time is always getting later and later and later. This is the flow of time, or the progression of time. That is what Larson calls a scalar motion, a motion that has a magnitude but no particular direction. Time isn't really flowing in any particular direction. It's just flowing with a certain magnitude or a certain speed. Speed isn't quite the right word, but magnitude. But space also has this quality. That would be the progression of space, or what Larson calls clock space, clock time and clock space. And clock space means that everything is always getting farther and farther and farther apart. And you can see that in the progression of the distant galaxies, or recession of the distant galaxies discovered by the Hubble telescope. But you can also envision it just with a balloon and a magic marker. Put a bunch of dots on the balloon, you blow up the balloon, all of the dots are moving away from each other, but in no particular direction. So that is the scalar flow of space. Space and time also have their discrete units. So there are minimum units of both space and time. They come in chunks. Exactly one chunk of space in one chunk of time is the speed of light. And so the speed of light in Larson's system represents the midpoint of the universe. Half of the universe is moving faster than the speed of light, half is moving slower. This contrasts sharply with Einstein's dictum that the speed of light is the maximum speed of the universe. That's because he didn't know anything about the faster than speed of light half of the universe. Larson refers to this half as the cosmic sector, and he refers to the slower half as the material sector. So we know quite a bit about the material sector because that's where we live and we observe and we measure from the material sector. And so all of our kind of legacy science knowledge comes from the material sector. But we know very, very little about the cosmic sector. But because of Larson's reciprocal postulate between space and time, all we have to do to understand what's going on in the cosmic sector is to extrapolate from the material sector. What's going on in the cosmic sector is exactly the same as what's going on in the material sector on a grand scale, except that you have to invert the roles or reverse the roles of space and time. So in the material sector, we have coordinate space, three-dimensional space, and we have clock time, the progression of time. But in the cosmic sector, we have coordinate time, three-dimensional time, and clock space. Space is always getting later and later and later. So that's how you can extrapolate what you know about the material sector and place it into the cosmic sector. Now, there are a few caveats that have to do with our position of observation. We're observing from the material sector, so we have to account or compensate for the fact that observing into the cosmic sector, we are going to only get there's a certain amount that's going to be lost in the translation. Being able to see across that speed of light boundary. Okay, now in Larson's system also, we're looking at, we're starting to look at his book here called Nothing But Motion. And this book is primarily about atomic physics. And just to give you a little background about atoms for Larson, is that an atom or matter is a combination of motions. And those combinations that starts out with a photon. The photon is the original thing that you need in order to get started building an atom. As a matter of fact, you need two photons that are basically directly out of phase. And a photon is itself a combination of motions. In Larson's system, a photon is a combination of a translational motion and a vibrational motion moving perpendicular to the translational motion. The combined motion represents a sine wave or a simple harmonic motion, and that is the photon. Now, some of Larson's followers have disputed that and said that the simple harmonic motion is the result of a combination of two counter-rotating motions. That also is a controversy that we will cover eventually. I tend to think that the double birotational model works better. We'll look at Dr. KVK Nehru's paper on the birotation of the photon sometime pretty soon. But so once you have the photon, then the photon can be rotated. And it can be rotated in a couple of different dimensions. So you have two different rotations of that simple harmonic motion, and that constitutes an atom. And then you have an optional one-dimensional rotation or a spin that also can be involved in that atom. And then, you know, obviously, if you're talking about the cosmic sector, a cosmic atom, or what the legacy scientists call antimatter, cosmic atoms are a reverse of that. So in the material sector, the photon is in time and the rotation of the photon is in space. In the cosmic sector, the photon is in space and the rotation of the photon is in time. Okay, now we're about to start chapter 18 of this book, and it's called Simple Compounds. Now, here Larson gets into organic chemistry. Okay, we already, covered subatomic particles and atoms and cosmic atoms, and now we're getting to compounds. So this is, molecules, how atoms fit together to form even more complex structures. And Larson has 4 or 5 chapters here at the end of the book on this chemistry, organic chemistry, and I don't know that we're going to read all of these, but we're going to start and probably try to at least get through this first chapter on simple compounds. Okay, here we go. In the preceding chapters, we have determined the specific combinations of simple rotations that are stable in the material sector of the universe. And we have identified each of these combinations within the experimental range, with an observed subatomic particle or atom of an element. We have then shown that an exact duplicate of this system of material rotational combinations with space and time interchanged exists in the cosmic sector. And we have identified all of the observed particles that do not belong to the material system as atoms or particles of the cosmic system. To the extent that observational or experimental data are available, therefore, we have established agreement between the theoretical and observed structures. So far as these data extend, there are no loose ends. All of the observed entities have been identified theoretically, and while not all of the theoretical entities have been observed, there are adequate theoretical explanations for this. The number of observed particles is increased substantially by a commonly accepted convention which regards particles of the same kind, but with different electric charges, as different particles. No consideration has been given to the effect of electric charges in this present discussion, as the existence of such charges has no bearing on the basic structure of the units. These charges may play a significant part in determining whether or not certain kinds of reactions take place under certain circumstances, and may have a major influence on the details of those reactions, just as the presence or absence of concentrations of kinetic energy may have a material effect on the course of events. But the electric charge is not part of the basic structure of the atom or subatomic particle. As will be brought out when we take up consideration of electrical phenomena, it is a temporary appendage that can be attached or removed with relative ease. The electrically charged atom or particle is therefore a modified form of the original rotational combination rather than a distinctly different type of structure. Our examination of the basic structures is not yet complete, however, as there are some associations of specific numbers of specific elements that are resistant to dissociation and therefore act in the manner of single units in processes of low or moderate energy. These associations, or molecules, play a very important part in physical activity, and in order to complete our survey, of the units of which material aggregates are composed, we will now develop the theory of the structure of molecules and will determine what kinds of molecules are theoretically possible. The concept of the molecule originated from a study of the behavior of gases, and as originally formulated, it was essentially empirical. The molecule, on this basis, is the independent unit in a gas aggregate. But this definition cannot be applied to a solid, as the independent unit in a solid is generally the individual atom, or a small group of atoms, and in this case, the molecule has no physical identity. In order to make the molecule concept more generally applicable, therefore, it has been redefined on a theoretical rather than an empirical basis, and as now conceived, a molecule is the smallest unit of a substance which can theoretically exist independently and retain all of the properties of the substance. The atoms of a molecule are held together by interatomic forces, the nature and magnitude of which will be examined in detail later. The strength of these forces determines whether or not the molecule will break up under whatever disruptive forces it may be subjected to, and the manner in which certain atoms are joined in a molecule may have an effect on the magnitude of the interatomic forces. But the determination of what atoms can combine with what other atoms and in what proportions is governed by an entirely different set of factors. In current theory, the factors responsible for the interatomic force, or bond, are presumed to have a double function, not only determining the strength of the cohesive force, but also determining what combination can take place. The results of the present investigation indicate, however, that the force which determines the equilibrium distance between any two atoms is identical in origin and in general character, regardless of the kind of atoms involved, and regardless of whether or not those atoms can or do take part in the formation of a molecule. Experience has indicated that it is advisable to lay more emphasis on the independence of these two aspects of the interrelations between atoms, and for this purpose the plan of presentation employed in the first edition will be modified in some respects. As already mentioned, the information that will be developed with respect to the molecular structure will be presented before any discussion of interatomic forces is undertaken. Furthermore, present indications are that whatever advantages there may be in using the familiar term bond in describing the various molecular structures are outweighed by the fact that the term bond almost inevitably applies the notion of a force of some kind. Inasmuch as the different molecular bonds merely reflect different relative orientations of the rotations of the interacting atoms and have no force implications, we will abandon the use of the term bond in this sense and will substitute orientation for present purposes. The term bond will be used in a different sense in a later chapter where it will actually relate to a force. The existence of molecules, either combinations of specific numbers of like atoms or chemical compounds, meaning compounds is a synonym for the existence of molecules, either combinations of specific numbers of like atoms, or chemical compound. Oh, okay. I think I'm messing up this sentence here. It's a pretty long sentence. Let's try it again. The existence of molecules, either combinations of specific numbers of like atoms, or chemical compounds, which are combinations of unlike atoms, is due to the limitations on the establishment of interatomic equilibrium that are imposed by the presence of motion in time in the electric dimension of the atoms of certain elements. Those elements whose atoms rotate entirely in space, or which are able to attain the all positive status by reorientation on the 8 minus x basis, are not subject to any such limitations. An atom of an element of this kind can establish an equilibrium with any other such atoms in any proportions, except to the extent that the physical properties of the elements involved, such as the melting points or conditions in the environment, such as the temperature, interfere. Material aggregates of this kind are called mixtures. In some cases where the mixture is homogeneous and the composition is uniform, the term alloy is applied. There is a class of intermetallic compounds in which these positive constituents are combined in definite proportions. Copper, zinc, and copper 8, zinc 8 are compounds of this class. But the combinations of copper and zinc are not limited to specific ratios of this kind in the way in which the composition of true chemical compounds is restricted. The commercially important alloys of these two metals extend through the entire range from a brass with 90% copper and 10% zinc to a solder with 50% of each constituent, and the possible alloys extend over a still wider range. The intermetallic compounds are merely those alloys whose proportions are especially favorable from a geometric standpoint. A typical comment in a chemistry textbook is that the theory of the binding forces involved in these intermetallic compounds is very complex and is not as yet very well understood. The reason is that there are no bonding forces in these substances in the same sense in which that term is ordinarily used in application to the true chemical compounds. Okay, that's it. Tune in tomorrow. Thanks for tuning in today. Have a great day.